I think you just convinced me to do it. So I'm gonna make a demonstration in the shape of the Star Destroyer from the Star Wars,
That'd
and
be
I'll
cool.
make it float. How about
Yeah.
that?
Yeah, that'd be cool.
Our neighbor's choice.
Well, we want to have a fun science conversation today because everybody still wants to know, have we reached the limit of the way in which we consider transportation, particularly space travel? Is there more things on the horizon that people could explore and discover? That's the question we have today. And to do so, of course, whenever I interview any topic or any guest on the matter of science, I like to have our chief science advisor, physicist Dr. Yu, with us. How you doing, sir?
I'm very good. Thank you for having me on.
Good to see you, and did a great job on the Tim Pool show. So congratulations for sharing a lot of the insights that you have with that audience. And then I also have a great scientist himself. He's from, you used to teach at UPenn, right? University of
Penn State.
Penn State.
Mhm.
Penn State, and he's a computer engineer, nuclear scientist, also investigates all kinds of scientific topics on the vanguard of science. Dr. Max Fomitchev-Zamilov. How you doing, sir?
Good. Thanks for having me.
Great to have you on again. And I just wanted to have you on because there's this idea that you've been talking about, and others have talked about this similarly, about could we have levitation, right? Levitation, anti-gravity, people use different
Yes.
words. How would you describe the idea that you've been mulling about in your mind?
I think the nature already solved all problems, and Earth defeats gravity routinely every day. We see clouds floating, we see spiders floating, and all of that is done naturally without any expenditure of energy. And I see no reason why we cannot be harnessing the same idea, the same principle, to move ourselves about this planet in a
Well,
green and energy efficient way.
very good. So tell us about what your idea is, because we're gonna let Ted turn it over to you in just a second to show us a presentation. But give us an overview of what we're about to
Yes,
see.
so the general idea is very simple. Earth has an electric charge, and I say we need to harness the power of static electricity, that is the Coulomb repulsion between the charges of same size, to counterbalance gravity and achieve levitation by way of Coulomb repulsion for transportation. And I'm going to show by going through my slides how it is done in nature, how nature is doing it now, and how we can be doing it. It's very simple, very technologically not challenging. So I'm frankly amazed nobody thought about it, before, because I think it can be done, very quickly and very cheaply. Uh, just to demonstrate the proof of concept and to go into commercial applications of it. All right, so I might as well start. So just for the sake of completeness, my name is Max Fomitchev-Zamilov. I have a PhD in computer engineering, and for many years I've been a professor at Penn State until I quit the university to start my own business. I currently operate Maximus Energy Corporation, and within this company, my main business activities, I manufacture, repair, and refurbish scientific equipment with the particular emphasis on radiation detection, neutron and gamma detection. But I also conduct all matter of research, be that nuclear fusion, electrostatic levitation, archaeology, whatever fancies me. So today I'm going to talk about electrostatic levitation and how we can harness this principle for transportation. Basically, what everybody knows what levitation is. Levitation is when something can float up in the air, and usually some mysticism is associated with it. We see yogi levitating, or various superheroes from comic books levitating. So there is an aura mysticism around it. But there is nothing mystical about it, because nature does it all the time, because levitation is not some kind of a secret force or anti-gravity. In its simplest form, it's a matter of static electricity. So we are surrounded by static electricity all around us. You take your sweater off, your hair gets charged, you walk on a carpet, your feet get charged and sparks jump. So static electricity is all around us. It's easy to generate. It has rather long range interactions by way of Coulomb forces. And all of that is very useful for both scientific and industrial applications, because electric force is such a strong force. So compare it to gravity, electric force is some 30 orders of magnitude stronger. So if you want to create a gravitational force of ponderable nature, you need a humongous mass that of Earth or of Moon or of Sun, huge masses. But if you are going to create a similar force using electricity, static charges, all of a sudden you need a amount of charge that's 30 orders of magnitude less than the amount of mass you need to create, same strength gravitational force. So we're talking about small charges on the order of picocoulombs or microcoulombs creating significant forces. And the reason practical levitation is possible is because Earth itself is electrically charged. This is not a controversial fact. It's a very well-known fact, but it's often overlooked. I would say, most people are not aware of the fact that when we're walking on the ground, that our planet is not neutral. It's in fact electrically charged. So under normal circumstances, the ground that we walk on has a negative charge, and the positive charge resides high above, over the clouds, in ionosphere. So you can say that this blue planet forms a spherical capacitor. The outer layer of that capacitor is ionosphere that's positively charged to a potential of about 300,000 volts, 300 kilovolts. So that charge happens to be there because Earth is basked in solar radiation. Solar wind blows constantly. Charged particles from the sun bombard our ionosphere every second, every minute, every day, every hour. And those charged particles create charge that's high up in ionosphere, that positive charge. And by way of electrostatic interaction, that positive charge creates a mirror charge on the surface of this planet. And that's a negative charge. So scientists estimate that the total charge of Earth is negative million coulombs. And the field on the surface of this planet is about 10,000 volts per meter. So it's a very significant field, very strong field, very meaningful field. And you can say, well, how come we don't feel it? Well, because the gradient of that field is not great. Typically, we feel fields or forces when there is a big gradient, meaning a huge change. But although this field is very strong, it doesn't change very sharply. That's why we normally don't feel it. Yet, there are places on this planet where you can actually feel it. And I don't know if you've seen videos on YouTube, but some people go to deserts, and deserts are so strongly charged, occasionally that hair will stand.
Wow.
And you will hear this electrostatic crackling. So that happens naturally in certain places. So in some places, the field is a lot stronger than this average that I'm talking about. But, it happens without, just by itself. It's a part of nature. And the other thing, worth mentioning is that, this electric field is tracked currently, specifically by airports, because airports have electric field meters and they're able to tell what is the lightning activity, because when the lightning strikes, it discharges the field. And if the sensor at the airport detects too many lightning strikes, they will call a halt on air traffic because there is a lightning threat. So this field is easy to measure. It's measured routinely. And as I said, it's measured primarily by the airports to assess the thunderstorm or lightning strike danger.
Right.
And what happens is when you have thunder clouds come in, so those clouds are also charged. And the charge in those clouds affects the charge on the ground. So when a huge thundercloud comes in, all of a sudden the charge on the surface becomes positive, and that you can detect. So that's the illustration here. So we're living in this very dynamic environment of planet Earth, where ground is primarily negatively charged, but depending on what the weather is and on how clouds behave, this field can change polarity. And that's exactly what I'm saying. We need to take advantage of this field. We need to put it to work. So how can we, put it to work? Sure.
Can you go back to page?
Yes.
Did you use a divide sign? Is that a 100 divided by 300?
100 to 300. It's not a division. I meant to say from 100 to 300. Yeah.
That's the okay. From 100 to 300.
Yes.
Okay. Yeah. The sign I thought it doesn't make sense.
You use a different character.
Got it. Okay.
Sorry. Okay. So we see the manifestation of so here I'm talking that the Earth is electrically charged and the clouds are electrically charged. So we see the manifestation of this electric activity by just looking up at the sky. We see clouds floating. And if you ask anybody, a physicist, a meteorologist, why the clouds are floating, and they will tell you, oh, because there's airflow. Well, there is only partial truth to it. There are ascending and descending airflow, but the vast majority of flotation that the clouds experience is actually in static electricity. So droplets in clouds are negatively charged, and they're levitating in the electrostatic field of Earth. So the reason we get rain or fog is when the electric field at the ground is low and it's not able to push the clouds up anymore. So the clouds go down and become, surface clouds that we call fog. Or if the field at the surface is even weaker, those droplets will not levitate anymore and fall down, forming a rain. So it's plainly obvious that you see clouds floating is that, these electric forces are at work. And they're holding up, hundreds, thousands of tons of water up in the air, without any energy. It's floating because particles, droplets in clouds are negatively charged, and the negative charge of the Earth is pushing it up. So this is how inanimate nature is doing it. But the life on this planet also is able to take advantage of this electrostatic levitation. Right now, you're looking at a ballooning spider. So ballooning spiders have been known for, at least 100 years, maybe 200 years. And they were found on ships crossing oceans. And it was a mystery to sailors. How come, this land-dwelling spiders end up on ships thousands of miles from shore? And only recently that secret was cracked. So researchers captured the spiders and put them inside a metal box. And that metal box had two plates in it. There was a bottom plate for ground and top plate that was able, that could be charged. And when scientists started charging the top plate to create an electric field, spiders recognized that the electric field is forming. So spiders have some antenna or sensors in their body that are able to send static electricity. And when that field was strong enough, the spiders deployed a tiny thread of web, which was also negatively charged. And as soon as they did, it became a ballooning device. So the static electricity of the box pushed on the static electricity on the thread that the spider deployed, and spider started floating. And when the researchers turned off the charge, the spiders fell to the bottom of the box. So this was studied and reported recently in Nature. So we already see that animals like spiders are taking advantage of the fact that Earth is charged, and you can levitate by using this electric charge. So spiders are already doing it. So what prevents us from doing it?
Right.
So the key question is, okay, we know that the like charges repel. So how do we create static charges like on a daily basis? So besides rubbing a cat, walking on the carpet, or taking your sweater, your woolen sweater off. Commercially, static electricity is developed by way of Van de Graaff generator. And Van de Graaff generator is a system with rollers and belts. where there are two different rollers and a belt is going, through these rollers. And one roller is creating static electricity and the belt carries it to the other roller. And then there is a brush that captures the electricity and you charge something. So this is a very well-known system that can develop hundreds of thousands of volts and even millions of volts in static electricity. I figured out a different way of doing it, a simpler way, and I would say a better way, and it involves passing oil through a restriction, be that a filter or just a Teflon or a PVC pipe. So oil is a dielectric. Pipe or a filter is a dielectric. So what happens when you rub two dielectrics next to one against another? Well, you create charge separation. You have a static charge build up. And that's what I experienced in my experiments with fusion. So here you see my fusion reactor that's filled with oil. And you see that the surface of the oil is curved. It is curved because the oil possesses significant static electric charge. It was so huge that my static electricity meter went off limits, so I couldn't even read it, but I could sense it in my skin. I could see sparks flying, and I was able to create this charge because the oil was pumped through a filter, and the filter was a paper filter, and the oil acquired significant electric charge. So using this concept, it's possible to build a Van der Graaf generator where the belt and the rollers are replaced by a flow of dielectric oil, and that will build up significant electric charge that can be collected using a brush and imparted on whatever object you wish to charge. So this is what I consider enabling technology, because this is simpler and stronger than a conventional Van der Graaf generator. And by the way, this is the picture of a conventional Van der Graaf generator that I just described. So you have your two rollers and the belt, and the belt carries charges from one roller to another, so it's friction. But oil is the same idea, but instead of a belt, you have a flow of oil. There is another part of the enabling technology that already exists. And I'm talking about materials called electrets. So electrets are dielectrics that are able to store electric charge permanently. So Teflon is one, various waxes, carnauba wax is another, polyethylene, polypropylene. Basically, all plastics are pretty good electrets, because and you experience this on a daily, when you unwrap something and all of a sudden the wrapper gets charged, and good luck trying to peel it off your hands, because it carries so much charge. So these materials store electric charge naturally. They're very good at storing this charge. So we don't even need to develop these materials, because they already exist. We simply got to use them. And for the sake of being specific, charge densities on the order of microcoulomb per meter square are possible. And this is a pretty significant charge, as you will see from this example. So for example, say you have a car or some kind of a vehicle that weighs 1,000 kilograms. So the force of gravity on this vehicle will be 10,000 newtons. We all know mass times the acceleration of a free fall g, gives you 10,000 newtons is the weight or the force of gravity acting on 1,000 kilograms. So to lift this vehicle up in the air, you will need to counteract this force of gravity. And you can counteract it by charging the vehicle. So say you put the electret over this vehicle, you charge the electret, and if the electret is capable of holding 1 microcoulomb per meter square, it will take only 10 square meters of this electret material to counteract the force of gravity, because the field of the Earth is so strong. So how can you lift bigger weights? Well, you either increase the area, kind of like with a balloon. The bigger the balloon, the larger the lift. So here is the greater the surface area that you charge, the larger the lift. Well, the other opportunity, besides increasing the area, is of course increase the charge density. So we can develop other materials that can potentially store more than microcoulomb per meter squared. And it's microcoulomb per meter squared is what's available now. So if we put some R&D effort in it, who is to say that we cannot do 10 or 20 microcoulomb per meter squared? So the third opportunity is, of course, you create a static charge generator somewhere on the surface. Say the ground field is insufficient, or maybe you want to lift larger weights than 1,000 kilograms. Well, you can build this Van der Graaf generator, and you can charge it to greater static potentials, and then the electrostatic force that is going to project on the vehicle that you are putting up in the air, would be stronger. So you can use this, boosters, or even better. You all heard about, Bob Lazar, right? And his ideas. So when I first came across his idea of using radioactive isotopes for levitation, I thought it was preposterous until I realized that what happens when you have a rapidly decaying radioactive isotope. And for the sake of concreteness, I will say let's take polonium-210. So polonium-210 is a commercially interesting isotope that anyone can buy. I buy it for my research. Companies buy it, and they buy it specifically to defeat static electricity. So when polonium-210 decays, it emits a lot of alpha particles that will counteract the negative charge, let's say, that builds up on a roller of polyethylene wrap, that you're unrolling. But by the same token, if you just take a chunk of polonium-210 and let it decay, all of the alpha particles will leave, and what would remain is a huge negative charge on that isotope. And that huge negative charge will interact with the charge of the Earth and will produce a lift. Because here you're not storing charge, here you're generating charge in real time. So we had microscopic quantities of polonium-210. You can, let's say, deposit it on the surface of the vehicle or mix it with the electrolyte material, and you will have a nuclear means of static charge generation that's constantly replenishing as long as this isotope is decaying. And the charge generation is stupendous. So the lift that you're able to achieve with this is huge. And in fact, some would speculate that's what U.S. military might be already using on some of its black ops projects, which they have heck knows, but this is definitely plausible because really you need microscopic quantities of polonium. Like in this example, I say you just need 0.2 of a milligram to generate a meaningful lift force on the order of 10,000 newtons. So this is entirely possible. Another rather simple application is tunnels. So Elon Musk is digging tunnels. We're digging tunnels. What is so good about tunnels? Well, tunnels is a controlled environment. In a tunnel, you can control electrostatic field. You can install charges or charge generators either on the ground or on the roof, and you can create electrostatic field that's far stronger than the field on the surface of the Earth. And then you don't need nearly as much charge on your vehicle to counterbalance the force of gravity. And once again, when you're inside this vehicle, you will not feel that field. So it does not present any kind of health hazard or any kind of electrocution hazard because you're sitting inside a metal box that screens all electric fields, and the field is acting only on the surface of the box or the surface of the vehicle where your charges are. So in tunnels, it's possible to levitate weights far greater than 1,000 kilograms because you can control the strength of the field. What else can you do? I think I already talked about that. Well, you can launch payloads to space. So right now, when you launch a rocket, the majority of the mass is fuel. 95%, 98% of the rocket mass is fuel. And this is inefficient. But what if you used an electrostatic launch system? So all you need to do is charge the rocket electrostatically, either put a charge generator on it in terms of your polonium-210 or statically charge the rocket by way of electrets, and then create a humongous charge generator, be that Van der Graaf or oil-based Van der Graaf on the surface, and voila, you have an acceleration force that would accelerate your statically charged payload up in the air without expending any fuel. Conversely, you can use AC electricity, not just DC or static electricity. You can use AC electricity to achieve the same effect by capacitively coupling two standing waves. So basically, I'm talking Tesla coils. So Tesla coil generates significant AC charge, which changes polarity from positive to negative. So in principle, we can have two Tesla coils that operate in sync. So their frequencies are synchronized and they're developing charges of the same polarity at the same time. And these charges will repulse themselves from one another through Coulomb interaction. So you can have one coil on the surface and the other coil on your payload. And once you're able to synchronize them, you will be able to project the same, accelerating, but not electrostatic, will be electrodynamic force because of the polarity changes. But that's just, another possibility. Oh, and by the way, a rather interesting paper has been published where you can use laser-guided discharges through air to transmit electricity through ionic channels in the air. So you can use this to couple your Tesla coil transmitter to your payload that you're launching to space. What else? Well, even for deep space propulsion, you can use the same idea. Once again, I'm talking about propellantless propulsion. It's all by way of electric interaction, but you will need an ion beam to communicate the electrostatic force from your, let's say, power satellite to your payload. So you can have a beam of sodium ions or some other ions to establish this conductivity channel and communicate the standing wave. So I think this idea can, in principle, work even, for deep space travel, but without so much looking so much ahead. We can focus on applications on the ground. And on the ground, there is yet another thing we can do. We can do, tethered drones that are single wire type transmission using a Tesla coil transmitter on the surface. And the return basically through the air. And once again, it's a quarter wave standing wave by way of Tesla power transmitter on the surface. And a single wire, a hair thin wire, could be powering an electrostatic DC motor on your drone. So that's yet another application of static electricity that could be exploited for payload maneuvering where tethering isn't a problem. So there is so much we can do if we just started engineering around static electricity. And this is something that's we typically trying to overcome because we think of static electricity as a parasitic and negative effect. And we spend money and engineering effort trying to get rid of it. But if we started leveraging it, there is quite a bit that we can do. What else am I going to say? I think I kind of said enough about it. So maybe it's time, for you to ask some questions.
Yeah. Is there anything else you want to show on the slideshow, or?
I think I pretty much covered everything. So
Yeah.
I would say the point of this presentation is I really want to raise the awareness of engineers that there are other ways to approach common engineering problems than the textbook ways. And the textbook ways we've been taught is, dynamic electricity. So static electricity overlooked or is considered a nuisance. Or we are hell-bent on using reactive force that requires propellants and fuel. And I'm saying all of that is not necessary if we just give static electricity a chance, if we give ideas of Nikola Tesla a chance, because you can have tethered drones, you can launch projectiles to space without without any propellant if you just engineer it around static electricity. And that's why I wanted to make this presentation. So I put it all in public domain, for everyone to use. I do not intend to take any patents on it, because why? Anybody can do this. And I want, somebody to take this idea seriously.
That's fantastic. I really appreciate you sharing this idea with our audience.
Sure.
We like to have a kind of, science meeting house on our show where people can share their ideas that they've put together, and you've done a great job exploring this.
Oh, thank you. Yeah. So
I-
basically, Earth has electric charge, and we got to make that charge work.
yeah, it's
And
kind of reminds
animals.
you of what Nikola Tesla was talking about, right?
Yes, he was talking about that quite a bit because he knew that this planet is very, very electric, and we see this every day. Well, right now we have a thunderstorm. That's electricity.
Yeah,
So the planet is telling us it's charged. It has this electric power. All we have to do is use it, and that's what I'm saying.
yeah.
Spiders use it. Clouds use it. What stops us from using it? So it takes available technology. So we're not talking, years and years of engineering. We're just talking applying uh, technology that's available today.
Dr. Yu, would you like to reference anything on the slideshow, or are you done viewing it? We can end it if so in
Oh,
the slideshow.
yeah, the slideshow is good. You give some background. Just say for what you show here, spider. What's the spider web? The thread. What that thread do here,
It's electrically charged.
right? So is this thread hanging on in the air or hanging
It's
on
basically
something?
hanging off the spider. So the spider exudes this thread. And
Right.
because this thread is electrically charged, the
Uh-huh.
electric field of the Earth is pushing it up. So the spider is hanging from this thread, kind of like like a basket from a balloon,
Okay.
except that there is no hot air balloon that there is this charged thread, but it's the same principle. So this charged thread is ballooning the spider up.
Do you have any models can demonstrate this static concept?
I was thinking about, doing this, and that's why, I made this presentation. One of my friends approached me and said, "Hey, I know this, wealthy guy who is interested in levitation. Why don't you write a proposal?" So that's why I put the slides together and say, "Hey, if you give us some money, we can actually put the demonstration together." I have all of the necessary components. I just could use help building it. So this past year, I have not been doing much of research and development, unfortunately, for a couple of reasons. Mostly because I've been very busy with my equipment making business. So I've been, making this, hardware for people to use for their nuclear physics experiments. And the other reason is, the older I get, the more difficult it becomes for me to make stuff. So I could really use a technician, to help me work on this project. So that's why I said, okay, well, if this guy will give us some money, we can put a demonstration together. So basically build a larger version of this oil-based Van de Graaff generator. Because the picture that I showed you here, so I have this generator, by the way. I have this Van de Graaff generator, but it's not very good. It's not very reliable system. So you don't want to use that, for practical purposes because belts wear off and rollers wear off. So I did a lot of experiments with it. It's no good like for demonstration. So that's why I want to make this different kind of oil-based. But right now it exists as a part of my fusion reactor. So I need to build a new one using a dedicated oil pump and a dedicated brush system. And that's what I need the technician and help for, because every day I think about doing it, but every day I'm busy with something else. it's like you have a job, you have life. So I have a job, I have customers, I have bills. So I never get around to do it because there is always other things in the way.
That's like Dorothy singing about somewhere over the rainbow, right?
Yeah, I mean that's why I put this proposal. So if
Yeah,
somebody could spare a little bit of money, which means I can quit doing what I'm doing and I can focus on and build this.
yeah. Good. Can you go back to the one which shows the platform for space?
Sure. Basically, even I talked to not Blue Origin, the other company. Uh, what was it? The Virgin Galactic. So I talked to Virgin Galactic about this idea of launching
Yeah.
payloads through Tesla drones. And that was all a very good conversation until the company closed down. And this is another interesting thing. There were a lot of papers written on it. So here is the idea: is high altitude launch saves fuel. So here I'm not proposing that you get rid of fuel altogether. Here I'm proposing that you lift your launch vehicle, let's say 10 kilometers up in the air, and you do a launch from 10 kilometers. And that allows saving some fuel, and that saving of fuel actually doubles the payload to low Earth orbit. And this is not my math. This is someone else's math. This has all been published, and this is all has been known. But I'm proposing a practical way of doing it. So you can build a tethered drone using commercial electric motors and lift your launch missile, 10 kilometers up in the air. And it's possible to transmit this power because the wire that you need for it is hair thin, because you're transmitting in a very high voltage, very low current. And that's why the weight of your tether is negligible. So that's why I think it's workable.
So when do the people? At what point do the people get inside the rocket? They get it on the ground floor or something?
Yes, and you just lift the rocket. So instead of using chemical propellant to boost the rocket to 10 kilometers, you use this electric power drone to lift the rocket.
What
and
would
you
be
supply power from the ground.
What would be the various safety variables that would shy away from this? Is there any downsides safety wise?
Not really. No, I looked at this quite closely a couple of years ago. There are commercial motors available, like Siemens motors, that are capable of 100 kilonewton thrust, 1.5 meter propeller. So you can put a few of this, and that will be enough to lift a 100-ton vehicle. And the only thing that was questionable until I showed how it could be done is how do you transmit power? Well, you transmit power by way of a Tesla coil that's connected through a hair-thin tether to this platform. And that's possible because you're not communicating much current. You're communicating only maybe 10 amps. And for 10 amps, you can use a commercial fishing line, which is just a few millimeters. And it's super, super strong, and it's not going to tear when it's extended to 10 kilometers. So that's what makes it possible. So you communicate conventional electric power, but very, very high voltage and very, very low current to this platform. And on the platform, you have a converter that goes from high voltage to low voltage, or better yet, you go from low voltage, high current motors to high voltage, low current motors, which is this slide.
Now, the 10-kilometer altitude, is that what does that compare with like air traffic?
You don't launch from anywhere. You launch from spaceports. So,
right. No, I'm just saying, like, just to give people a sense of scale.
We launch already. We launch from Star City. We launch from Cape Canaveral and from a bunch of other places. So this airspace is cleared for this.
No, I'm not saying about real. I'm just saying to give the audience an understanding of like how high it is. Yeah, just to give.
That's about 30,000 feet. So that's
is where planes are usually flying, commercial jets.
Yeah.
Okay.
So that's kind of the altitude we want to get the payload to. So we have a high altitude launch. So I think this is a feasible idea and doable if somebody wants it done. Here we go.
All right. Well, Dr. Yu, any questions or thoughts you have?
Just capacity. So how much weight you think require, how much input to make, say, if we want to launch a capsule, use a static. Right now we have a demonstrated device called the electromagnetic launching, right?
Mm-hmm.
Yeah, that's something it's already applicable in many applications, right? So how mature do you believe this technology can be?
Well, it can be made mature if we invested in research and development. So right now it's at the concept stage, right? So I just showed that it could be done. But from this point on, it needs to be developed. And we don't know what challenges, might appear. So I'm just presenting a concept at this stage. So it's at the first level. And whether it's going to get to the next one depends on, if anybody needs it. So I figure I'll put it out there, and then whoever needs it, they can take it and, run with it. That's kind of the way of science. Yeah, you have an idea, you publish it. And this presentation, constitutes a publication. So anybody who will find it interesting, they can build on it.
Is there a way to do airplanes that way where you have them electrostatically traveling across?
Sure. I mean, you can basically, let's say, deposit an electret coating on an airplane, and you can charge it, and that way you produce lift. So it's the same idea as, let's say, hot air balloon, right? So in hot air balloon, you have this massive balloon that's producing lift. In the case of static electricity, it's the coating and the surface area. So in a way, yes, you can make a balloon, or if you can have just large surface area that's not necessarily closed, it will have the same effect. So yeah, I mean, you can coat the airplane, and it will take less fuel to fly, because all of a sudden you don't need to combat the force of gravity, because the static electricity is pushing you up. Or if you combine this, with radioisotopes, then it's even better, because then you replenish the charge without any mechanical means.
Oh, and there's such a lack of innovation in the aerospace industry. I wish you could,
Well, I wouldn't say that. I would say a lot of innovation is not spoken of because it's done, by the government or by the military.
the airplanes, yeah.
Yeah. So who
But I
the heck
mean, in the
knows what
commercial
they're doing?
sense of the public's awareness of it, there's just not. We have pretty outdated technology for the public. Yeah,
Yeah, and there is a reason for it, and
Yeah.
unfortunately, it's across the board. And I know the reason for it, from my days with the heavy oil upgrading. So some of these industries, like oil production or airplane or radio, are very heavily regulated, and this heavy regulation imposes disproportionate punishments on companies for failures, and that discourages them from trying new things severely. So oil companies keep using 100-year-old, 150-year-old refining technology because it's proven. And if they do something unproven, and then an accident happens, the fines and problems they get so much outweigh, the benefits of innovation, that they are reluctant to do it. And air traffic is the same way. And it's bad enough, publicity of recent catastrophes, Boeing having troubles and doors blown away. Even conventional technology, it's hard enough to keep up, right? And you say, oh, let's try something new. And by the minute, execs hear this, they say, we are in enough trouble as it is. So there's no incentive for them. It's just the overregulation basically drives out the innovation, because now you just want the same thing over and over and over, because it's no problem. And any kind of new thing is a potential problem. So
yeah.
I understand it.
Yeah, Dr. Yu, what do you think of this idea of being able to dramatically reduce the payload of rockets by using electrostatic to do much of the lifting past Earth's atmosphere, so that you can just focus on the space part of the journey, and then even using that technology in space? I like the idea of fighting smarter, not harder. And whenever you have to load up tons and tons of combustible fuel, you always think, man, is there a way we could make this more efficient?
Yeah, if you have a tabletop demonstration, use instead of try to build an industrial level something, just like something, just a couple, very small stuff. You can demonstrate how this one works. That gonna be that will be able to help you to say, hey, people, look at this one.
Good idea.
Yes, it'll work, and then we can scale up, right? You have a small model, just use handmade, and then to demonstrate the effect. I do have a called a static electricity generator. Is that you can see it can lift. If I have a balloon, right? I use underneath the balloon. You can see the balloon can float away from the static stick. Something you can say, hey, demonstrate the principle, right? Just
very good idea.
Household stuff, and then people can imagine. So how much effort if we can just scale up, then
Excellent
that would
idea.
I
think I'm gonna do it.
The case.
I think you just convinced me to do it. So I'm gonna make a demonstration in the shape of the Star Destroyer from the Star Wars. And I'll make it float. How about that?
Yeah, that'd be cool. That sounds like a future episode I'm looking forward to already.
Yeah, I'll do that. I'll do it in the shape of Star Destroyer. Yeah,
Yeah,
that'll be fun.
people love to see those demonstrations. That's what sells people on the reality of something.
Consider it done. I'll work on it.
I when I do we have a Kennedy Space Center have a family day, some open center, right? I use an electromagnetic launcher. I'm handmade one, and you press it, and then it can heavy magnets. You can see the shoot
Right.
to the roof.
Right.
Yeah,
Shoots
so then
up.
people know. So this technology is there, as long as you scale up to right now the rocket launch, 97% of the
It's fuel,
entire
yeah.
weight is
Yeah.
for propellant,
Yeah.
right? And for the rocket itself, it's not for the capsule.
Yeah.
So that means if we use electromagnetic launcher, you do not basically you have infinite power. Yeah, of course you don't want it to accelerate too fast. However, if you send if no astronaut, no human human being on board, you can shoot it up. It's very very economical. And this is nothing more, just like an electromagnetic gun shooting bullets, right?
Yep.
They can shoot in as high as a ton of something, something, and that one. So that means there's no problem with electromagnetic.
Right.
idea. Now you use a static.
Mhm.
If you can make a static work, even greater, I believe that application can be a much broader application, right?
Yeah. Well, I'll work
Now
on the
just
demo
like-
as you suggest.
Yes.
I'll do the demo.
Hope next time you can show up. I believe the principle should be pretty simple to demonstrate, right?
Yes, you're absolutely correct.
Electrostatic repulsion.
Yes.
Right.
I'll do that.
And so is the secret in being able to control it safely and everything, lowering it, raising it.
Of course,
thing?
yes.
Yeah. That's the secret, right?
The difficult part, you demonstrate the electro repulsion. That's the easy part. The difficult part, how do you use the static electricity against the gravity pull, right? Without additional electro generator assistant. So how you make this material create a static charge and against that. If you can make that one, man, you're gonna have a entire on different class.
Well, I'll work on it. Thanks for your encouragement.
I appreciate you guys.
I know you are one of the few, top engineer scientists alive. So I hope if anybody can be successful, you can, right?
All right. Well, thanks. That's very kind of you. Thank you.
Yeah,
for
I'm
your
I'm looking forward to our follow-up on this episode. So I appreciate you guys for coming on. Any last thoughts or statements you want to share?
No, keep up the show going.
Thank you. And you too, Doctor. You keep going what you're doing too.
Thank
Sure.
you. Thank you.
Well,
Yeah.
take care, guys.
Take care.
Where art is a man? What has he got? If not himself, then there's not to say no.